Hi everyone, welcome back to Physics Wala. Friends, in today's class we are going to continue our chapter Electric Charges and Fields, and this is going to be the third lecture. Hopefully you enjoyed the first two lectures. In this lecture we are going to talk about electric field lines, their property, electric field intensity due to a point charge, due to a ring, and we are going to basically define what do we really mean by electric field intensity, right? So let's first try to understand what do we really mean by electric field. Dosto, do you remember we have also talked about gravitational field in the chapter of gravitation, right? So whenever we come across a non-contact force, whenever we come across a force which we can't see, which we can only observe, right, those forces always comes with their field, right? The field is actually a type of a field is actually a region in our space. In that region a particular body can apply a force on any other body. So this is a basic idea. So we are going to define electric field in a similar way. We are going to say electric field is the space surrounding an electric charge small q in which another charge q dash experiences an electrostatic force of attraction or repulsion. It's a very easy definition, right? So basically when someone is going to just talk about electric field, so electric field is nothing but it is a space surrounding, right, space surrounding a charge. And that's why when you want to actually define electric field, mathematically, when you want to define electric field mathematically, we are going to define it in two ways. One, we are going to use the concept of intensity of electric field, that is intensity of electric field, and this is a vector quantity denoted by E vector. So it has got magnitude as well as direction, right? So intensity, this whole chapter is about intensity of electric field, so you don't have to worry about it. The second thing is we can also use electric potential to define electric field. So electric potential, as you guys know, we are going to start electric potential after we finish this particular chapter of electric field, right? So electric field is simply a region. This thing is simply a region or space. This is simply a region or space surrounding a charge, right? And if you want to know more about that, we'll define it using intensity of electric field or electric potential. So this is the basic idea behind the electric field, and we'll start our class with intensity of electric field. How do you define intensity of electric field? So what you can say is the electric field intensity at a point is the force experienced by a unit positive charge at that point. It is a vector quantity. Let me break it down for you, dosto. Let's suppose we want to know the electric field of this charge capital Q at a point P which is at a distance of r from this. This is the case. So what you are going to say is, you are going to say, let's assume that I have got a unit positive charge over here, which is often known as test charge. And let's calculate the force experienced by this unit positive charge. For simplicity, I am also taking this to be positive. You can take it in either way. Okay? So if you are going to take it as positive, the direction of electrostatic force will be something like this. So we are defining electric field as, the formula is defined as, electric field intensity is defined as the force experienced per unit charge. So F divided by Q naught. So this is the formula for electric field. Charge is a scalar quantity, force is a vector quantity, therefore electric field is going to be a vector quantity, and this means that the direction of electric field, is along force. So right now if force is in this direction, that means at this point electric field is also in this direction. Hopefully this concept is clear to all of you, right? So its SI unit is Newton per Coulomb. Absolutely, sir. Newton per Coulomb. There is also one more unit, that is volt per meter. Please remember it. We are going to talk about it again later. Its dimensional formula is given as, it's very easy. Dimensional formula can be found out very easily. We know that dimensional formula of force is m l t to the power minus 2. For charge, the dimensional formula is A and T, right? So you will have T raised to the power minus 3 and A raised to the power minus 1. That's it, right? Now let's begin. Let's talk about electric field due to a point charge. All right. So let's suppose we have got a point charge. Something like this, and similar diagram, my dear friends. And we want to know the electric field at, let's say, at this point, at a distance of r, we are going to place a q naught charge plus 1 coulomb. So the force experienced by this charge will be, force is going to be simply k q naught divided by r square. So electric field at this point will be k q by r square. That's it. And if you want to write down this in vector form, it will be, electric field will be written in vector form as kq by r square dot r cap. That is, electric field will be radially outward from a positive charge. In this class only we are going to also talk about direction, but for now, if you want me to draw the graph, please remember, for a point charge, electric field is, the graph of electric field will be something like this. That is, electric field is inversely proportional to r square. Hopefully everything is clear, my dear friends, right? Now let's discuss electric field due to a ring. All right, electric field due to a ring. Done. So let's suppose that first of all, let me draw a ring for you. This is how a ring would look like. Please understand that ring is actually a one-dimensional body. That means charge is along the length, right? And it will look something like this, dosto. Charge is only at the length, only at the periphery. Please remember, ring is a one-dimensional object. Hopefully this is clear to you. Acha, we actually don't know anything else than a point charge. We know the electric field due to a point charge. It is kq by r square. Let's suppose we want to find out the electric field due to a ring at the center. So this is at center. Fine, sir. Done. Let's suppose that this ring is made up of infinite number of point charges, right? This is what we are saying. We are saying that this ring is actually made up of infinite point charges whose magnitude of charges are dq. This is the concept that we often use whenever we want to break a bigger thing. We actually say that it is made up of infinitely small things. So a ring is made up of infinitely small point charges, right? Or you can simply say it is made up of infinite point charges. That would be more right. Acha, what is the distance of these this point charge dq from the center? So you are going to say, sir, it is actually from center, it is at the distance of radius, that is r. Then I will say ki what is the direction of electric field? You are going to say, sir, if this charge is positive, direction of electric field is going to be towards this. So because this charge is also very, very small, sir, this electric field is going to be also very, very small, that is dE. Now you will ask me, sir, can you please write down how you are going to write down this dE? I am going to say that dE will be actually written as k into dq divided by r square, just like we wrote the formula for a point charge, similar to that. isn't it? K dq by r square. Absolutely correct, sir. Now what my logic is, I am going to say the point charge that you saw over here, you can actually saw a similar charge diametrically opposite to it. This is also a dq, absolutely sir, and this is also at a distance of r, absolutely sir. So because of this, the electric field will be something like this, dE, absolutely, because electric field is a vector quantity, it will get cancelled out. Yes, sir. That makes sense. So what I am trying to say is, because of symmetry, if you will choose a dq charge over here, you will also find a dq charge on the diametrically opposite point. If you will find a dq charge over here, you will also find a dq charge somewhere over here. In a way, when you are going to find out the net electric field, due to symmetry, it will come out as 0. The answer will be, due to symmetry, electric field cancels out and net electric field comes out to be 0. So, sir, this was actually very easy, isn't it? Right? This was too simple. All right, no problem. So, let's actually increase our level, and let's say now let's not find the electric field at center. Let's suppose that you have got a ring. You have got a ring, and this is the axis that we are talking about, the axis of the ring. Right? So, this is something like this. This is a ring. On the periphery, you have got charges, and this is the axis, something like this. And we want to find out the electric field at this point. Please try to understand. This is a ring, and at this point, we need to find out the electric field. So, let's suppose total charge is capital Q, radius is capital R. This radius is capital R, and from the center, let's suppose this distance is x, at which we want to find out the electric field. This is x. All right. Again, let's do the same thing. Let's say ki we have got some dq charge over here. So when you are going to join this dq charge with this, the electric field will be radially outward. It would be dE. Similarly, when let's suppose this angle is theta. So this angle will be theta. Absolutely, sir. You are going to find another diametrically opposite point over here. That is again dq. You are going to again connect these two charges, this charge with the axis. Again, because this was diametrically opposite, if this is theta, then this will be theta. And the vector, electric field vector will be drawn radially outward. And this will be also dE. And this angle will be also theta. Now, because of symmetry, I am going to simply, first of all, I am going to write, let's draw the component of this dE. So, it will be dE sine theta and dE cos theta. Then let's do the same thing with this one. So, it will be dE cos theta and dE sine theta. Now, what we are seeing is, due to symmetry, dE sine theta will get cancelled out. That means due to symmetry, the integration of all the dEy will come out as 0. That means the net electric field will be nothing but the integration of all the electric fields along x direction, and that is nothing but dE cos theta. Hopefully everything is clear. And what do you mean by dE? So dE is again k dq upon this distance is actually r square plus x square and root of it. So when you are going to square this thing down, you will get r square plus x square. And when you are going to integrate the whole charge, you will get simple kq upon r square plus x square. That's it. Alright, my dear friends, you could have also used another way. You could have also said, ki let's suppose sir, that this linear charge density is lambda. So lambda will be q divided by 2 pi r, and then you could also write down in the form of lambda, but this is absolutely fine. The total charge is q. Each charge will be at the distance of r square plus x square and root of it. So you can simply write it down and see this works. If x is actually equals to 0, you are going to get the electric field at the center, that is kq square by r square, right? Hopefully everything is clear. We have found out the electric field due to a ring at the center. Now let's move on and let's find out some of the properties of electric field lines. First, let's find out how we define these electric field lines. So electric field lines is something else. Electric field lines are actually some imaginary lines that we have drawn so that we can understand how to actually analyze these field lines. Okay? How to analyze field. So a field line is an imaginary line drawn in such a way that its direction at any point, that is the direction of its tangent, is same as the direction of the field at that point. What do we mean by this? We are going to understand. Field lines can also be used for comparing the magnitude of electric field intensity. The intensity of the field is proportional to the number of field lines crossing unit area at right angles. Electric lines of force have the following properties. I am going to show you the property, but first let me explain the first point. Let's suppose I have got a positive charge like this. And from this positive charge, if I will draw a test charge over here, we know that force will be in this direction. So in the direction in which you have got force, it's going to be the direction of field lines. So direction of field lines will be something like this, originating radially outward, right? So now let's suppose you want to find out the direction of electric field at this point. So this is going to be the direction. I mean, obviously, sir, what's so new about it? When we are going to have more than one charge, then this electric field lines will actually will actually serve its purpose, right? Now let's move step by step. First of all, these lines are imaginary and these are smooth curves. That means you are not going to have sharp turns. These are going to be smooth curves, right? So for example, as you are going to have electric field lines, let's suppose electric field lines something like this. Alright, or you could have electric field lines like this. So what is the difference between these two field lines? The direction of electric field at each of these points is same. Direction is same, that is in this direction. If you want to find out the direction at this point, draw a tangent. If you want to find out the direction of electric field at this point, draw a tangent. If you want to draw direction of electric field at this point, draw a tangent. Right? But at all of these points, direction is same. So these are imaginary and smooth curves. They can never intersect each other. Why? Because let's suppose you intersect the two electric field lines. What will happen is that at this particular point you can draw two tangents. One tangent can be drawn using this curve. Please excuse me for not drawing the tangent exactly, right? And the another tangent can be drawn something like this. So at a single point you are having two electric field lines, two directions of electric field, which is not possible. So never they can never cross each other. They never form closed loops. What do you mean by closed loops? When we are going to talk about positive and negative charge, always from a positive charge electric fields originate and on a negative charge it terminate. It will never come back to any charge, right? So they never form closed loop like in magnets. The number of lines originating or terminating on a charge is proportional to the magnitude of the charge. This thing means, I am going to explain it to you using, see, this is a diagram, alright. Let's suppose we have got charge Q over here, right? And when you are going to draw an area an area like this, you are going to say ki, acha, how many electric field lines are passing at right angle from this area. From this area would be 4 pi r square of this sphere, right. So let's suppose it is q and 1, 2, 3, 4, 5, 6, 7, 8 lines are passing. Now let's suppose I say ki instead of q, let's say that I have got 2q charge at this point. So what's going to happen is that instantly the number of field lines will get doubled. So now the number of electric field lines which is passing this area has gone double. This means that the number of field lines which will cross through an area normally is directly proportional to the magnitude of the charge, right. This also tells you that if let's suppose at a certain point, for example, as we know that electric field due to a point charge is inversely proportional to r square, isn't it? So this means that the point where the electric field lines are crowded, for example, as this point, electric field lines are crowded, right? So at this particular point, electric field intensity will be more as compared to this point. Let's see, I'll give you another example. Let's suppose you're drawing an area of 1 meter square over here. This is 1 meter square. How many electric field lines are passing? 1, 2, 3. Let's again draw 1 meter square at this point. How many electric field lines are passing? Only one. That means the more number of electric field lines are passing. This is also known as electric field density. If electric field density is more, in another way, if electric field lines are more crowded in a region, at that point field intensity is more, and it is governed by our normal formula, isn't it, right? So please, the important point is to remember that we are drawing an area and then field lines are passing through it, because later on we will talk about something that is called as flux. That means these terms are important, my dear dosto. This is area, not a loop, right? This is area. So again, for a negative charge it will terminate, for a positive charge it will originate. They will never come back. This will not happen that they are going like this. They are going like this and they are never going to turn back. If they would have turned back, then we would have said that they are forming closed loop. Right now, these are open, smooth curves. Alright, no sharp turn, open, smooth curve. Right. So hopefully first thing is clear. Imaginary and smooth curve can never intersect each other. My dear dosto, can never intersect each other, can never form closed loops. The number of field lines originating or terminating on a charge is proportional to the magnitude of charge. Electric field lines end or start normally at the surface of the conductor. You are going to learn this concept again in electrostatics, but we can understand it over here as well. What will happen is that let's suppose you have got a conductor like this. Let's suppose you have got a conductor like this. An electric field line is not originating normally, but it is originating at certain angle, right? So what will happen is that this electric field will have two components. One of the component will be normal, so we don't have any problem with this. The another component will be tangential or parallel to the surface. This electric field will actually apply force on the charges kept on the surface. So you have got charge on the surface. Now that's how the electric field is produced. On the surface or inside the surface, that's not the point. But if electric field is produced, that means you have got charges. And now if you have got charges and you are saying, sir, there is electric field along the surface, this means that because of this electric field there will be some force, because electric field is nothing but force divided by charge. So if you have got force acting on these charges will start to move, which will disobey the basic principle of electrostatics, that charges are always at rest, right? So this is why we say that only this electric field is permissible, not this. So electric field will never be at any angle other than 90 degree from the surface, right? So either they will terminate or they will originate If it is positive, then they will originate at 90 degree. If it is negative, then it will terminate at 90 degree. We are going to again talk about this concept in electrostatics. Tangent to the field line at a point in an electric field gives the direction of the electric field. This is also very, very important, right? We have talked about it. Now, this is something that is called as electric dipole. We are going to talk about, again we are going to talk about this in this chapter only. Electric dipole is not a big thing. It is a system of two charges. Hear me out. It is a system of two charges. Those two charges have equal magnitude and opposite polarity. Now, when you are going to draw the electric field lines of these two charges, it will be something like this, right? And these are open, smooth curves. From positive charges originates, on negative charges terminate. If you want me to know, if you want me to tell ki why sir it is like this, so just let's understand that we have got a positive charge at this point, a positive charge kept at this point. This plus q charge will actually repel it. This negative charge will actually attract it, and the net force will be in this direction, which is actually nothing but the direction of the tangent, right? So this is how we are actually making curves, right? So at any point, if you want to find out the direction, just draw a tangent at that point. You will get the net force and net electric field. Similarly, two positive charges electric field will repel each other, right? And near the charges, you have got greater electric field intensity, greater strength of the electric field because they are crowded. And at charges, always remember they enter at 90 degree. I mean, if it doesn't look like they are, but they do enter at 90 degree, right? Similarly, you have got another charge. Let's suppose you have got 2q charge and minus q charge. So you will have more crowded lines near the greater charge than the weaker charge. Very easy, no problem, right? So it's still there, open loops. Hopefully everything is clear till this point also. Now let's solve one or two questions. The first question is saying two positive point charges q1 and q2 are separated by a vacuum by a distance of 3 meter. Find the point on the line between the charges where the net field is 0. Net electric field is 0. These types of problems are known as equilibrium problems, neutral point problems, where they want us to find net electric field as 0, net electric field as 0. Acha, please tell me one thing. If net electric field is 0 at a point, obviously net force will be 0 at that point. So it means same, right? So these types of problems are actually known as equilibrium questions, because if net force is 0 at a point, that point will be actually known as equilibrium point. And then that equilibrium point can be of two types. It can be a stable equilibrium, or it could be an unstable equilibrium. If you don't recall what do you mean by stable or unstable, I'll give you an example. Let's suppose a body is in stable equilibrium. The word equilibrium basically means net force is 0, and to be precise, net torque is also 0. But right now we are going to only talk about force. So if something is in equilibrium, it means that it is in the net force is 0. Now stable equilibrium basically means that if we are going to disturb the position of that particle, there will be a restoring force which will act on the particle, which will bring back the particle into stable equilibrium. I'll give you a normal example. The normal example is something like this, dosto. Let's suppose you have got a seesaw type of a thing, and you have got a ball kept at ground. The ball has got mass m, mg is acting downward, normal reaction is acting upward, normal reaction is also equals to mg, and net force at this point is 0. So it is in equilibrium. Now let's find out whether it is in stable or unstable equilibrium. So let's disturb it. When you are going to disturb it, you are going to, let's suppose you are going to apply an external force in this direction. So when you are going to apply an external force in this direction, the body will go up and there will be a restoring force which will act in the backward direction. And this force will try to bring this body down, and when this will come down, it will start moving in simple harmonic motion. This type of equilibrium is known as stable equilibrium. Alright, what about unstable equilibrium, sir? Let's suppose you have got a body kept at this point. This is also equilibrium, mg and normal reaction. But if I am going to apply an external force in this direction, this body will fall down and it will never come back. It will never come back. This type of equilibrium position is known as unstable. There is also a third one which is known as a neutral equilibrium. Let's suppose you have got a particle over here. It is in equilibrium and you shift it and it comes back to a new position and there is no difference between these two. This is known as a neutral equilibrium, right? So hopefully you got it. What do you mean by stable? What do you mean by unstable? Now let's come back. So you have got 2 point charges, both of them are positive. So you have got 2 point charges, both of them are positive. You have got Q1 equals to 16 microcoulomb, Q2 equals to 4 microcoulomb, right? You want to find out the equilibrium point where electric field and force will be 0. They both mean same thing. Okay? Now, where see, these two charges has divided the plane into divided this plane into 3 parts. First is between these two charges. First is between these two charges, and second is towards the left of both of these charges, and the third is towards the right of both of these charges. So where will that neutral point will be? So again we are going to use a test charge for it. How? Let's suppose दोस्तों we keep a test charge somewhere over here. Test charge is always positive, you know that. So Q1 will actually repel this test charge because Q1 is positive. So this is how we are going to draw F1. Q2 is also positive. So Q2 will also repel it. So we are going to write F2. दोस्तों, you tell me, is there any possibility कि F1 plus F2 can become 0? Absolutely no. Why? Because they are adding up. So there is no possibility that net force can become 0 at this point. Similarly, is there any possibility that at somewhere over here the net force will become 0? Absolutely not. That means this question will serve as a concept to you. This means that if you have got like charges, always remember that neutral point or equilibrium point lies in between of charges. But can we also say that it will lie between, it will be nearer to which charge? Yes, it will be nearer to 4 microcoulomb charge, somewhere over here. Why is that, sir? Because of equality. See, this charge is of greater magnitude. If you think, sir, we want to keep it at the middle, this has greater force, this has greater magnitude, so it will apply a greater magnitude of force if you will keep them at equidistant point. You want to balance out the situation, na? And this is poor, weaker force. So you want to actually make the neutral point nearer to this charge so that they can balance things out. This is why it will be nearer to this point. And let's suppose this distance is x, the total distance was r, and if you want me to actually give you a shortcut for it, total distance is r, and let's say this is r1 and this is r2. दोस्तों, electric field due to 16 microcoulomb will be in this direction, that will be E1. For E2, for Q2 it would be E2, something like this, right? So we are going to simply say that magnitude of E1 will be actually equals to magnitude of E2. I am actually using the vector law, right? I should have written vectorly, I should have written that net electric field is actually equals to vector E1 plus vector E2. Hopefully everything is clear. And because the angle is 180 degree, they are cancelling out each other and I want to make them 0. So, I have equated their magnitude. So, it would be K Q1 upon R1 square equals to K Q2 upon R2 square. So, K and K gets cancelled out, right? My dear doston, shall I write this thing as R1 and this thing as R2 so that there is no confusion, because this is Q2, right? So, this will become Q1 upon Q2 will become, or I should say R1 upon R2 will become the root of Q1 upon Q2, right? So, that means R1 upon R2 will be under root of, hopefully everything is clear, under root of 16 divided by 4, that is 4 and that is 2. Further, that means R1 can be written as 2 times of R2, which makes sense, which makes complete sense. R1 is greater, R2 is smaller. Also, R1 plus R2 is actually equals to R. So, you have got two equations and now the distance between them was 3 meters. So, R1 plus R2 is 3 meter. So, I'll use 2R2 plus R2 equals to 3. So, R2 will come out as 1 meter. So, this is 1 meter. This thing is 1 meter doston. And this thing is 2 meter. So, this is a short, what is the short trick, sir, by the way? The short trick is, my dear friends, the short trick is that R1 upon R2 is equals to under root of Q1 upon Q2 for force or for electric field. Another thing is, this was for like charges. What will happen with unlike charges, sir? For unlike charges, it will be either on this side or on this side depending on the magnitude. Let's suppose this was 16 and this was minus 4. Or let's suppose this is minus 16 and plus 4. Now, which one has got lesser magnitude? Please don't say minus 16. When we are talking about magnitude, remove the sign. The sign, the uses of sign was just to know whether the equilibrium point will lie in between or on the either sides. Now they are unlike charges, so it will lie on the either sides. Now which side? This is minus 16, this is plus 4. The lesser magnitude is 4, so it will lie somewhere over here at a distance of x, right? Again, you can use the equations and find out the value, right? So hopefully, my dear friends, this was all good to you. The last problem is something like this. Although in this one they have talked about whether the electric potential is greater at point A or not. We are not going to talk about potential, we will talk about field. Now you tell me at which point field is greater. Obviously, sir, where the electric fields are crowded. So at A point, electric field strength is greater than B, definitely. Alright, so hopefully everything is clear with this concept as well. Now we will move towards the end. Hopefully you enjoyed today's session as well. We are going to come up with more questions in later classes. I've kept these classes to be around 40 minutes, 45 minutes. So we are trying to balance out theories with questions, but we'll keep some questions, some classes exclusively for questions as well, right? So I'll see you in the next class. Please take care of yourself. Have a nice day. Thank you so much. Bye bye.